Thanks, Jessie. There's my screen. Yeah, thanks. I'll be talking about, indeed, active WeaSuL, improving weak supervision with active learning. So yeah, another talk about active learning, but it's going to be a bit of a different perspective. And yeah, I will be showing what we've been working on for this research project and this paper. So yeah, I've been working on this with a great team, Rafa, Luis, Max as well, who's here, and Nana. So yeah. First about the context. So if you want to use supervised machine learning for a problem, you're going to need labeled data, and usually you need quite a lot of it. And yeah, mostly in recent years, a lot of efforts have been going into obtaining these huge data sets, such as ImageNet, that have enabled the development of bigger and more complex discriminative models. But what we saw in the previous talk as well, it can be quite difficult in many projects and applications to get enough labeled data, because quite often you need an expert in the domain to provide the labels accurately, and there can be quite privacy constraints, and yeah, it can just take a lot of time. So for this reason, yeah, it's really good to consider how to make the most efficient use of our domain experts, so that we can turn this unsupervised problem that you might have into a supervised problem. And yeah, there's a few options. Active learning, like in the previous talk, where we try to determine which part of the data would be most useful to get labeled. Or another option is to try and create sort of less precise labels that may not always be accurate, but they're really much faster to get for a larger part of the data. So yeah, then I'm talking about weak supervision. So I'll go a bit more into how that would work. And to do that, I will be using a very simple data example where we have these unlabeled data points. And actually the ground truth is also here, but we want to try and get labels using weak supervision. So to do that, we start by asking our experts to define a set of labeling functions. And these labeling functions, in this case, they sort of, based on some value of one of the features, divide up the input space so that they assign one class to one side and the other class on the other side. In this way, we try and collect a few different sort of rules that, based on the knowledge of the expert, encode how the data can be roughly labeled. So these labels will be less precise, but in one go, they provide labels for all of the data. But yeah, then once we have those, we basically have these different weak labels that are sort of contradicting, because they in different regions they may agree or disagree. So the next step is to try and learn how they can be combined such that we get one label. And yeah, we then learn how to combine them in using this generative model that essentially introduces this latent, this true label that we actually can't observe. So by learning this model, we are able to get probabilistic labels that are essentially distributions of this true label conditioned on the different values of the weak labels that were given. Yeah, I can't really go much more into how this model is learned, but it's from this paper here. So if you're interested in learning more, I recommend reading that. But now that we have learned to combine these weak labels into one probabilistic labels for our data points, we can actually train a discriminative model that uses those labels as supervision. So that was our goal. And this is also where we basically encountered a problem, because as you can see, with the labels that we obtained through weak supervision, we get this discriminative model with a decision boundary that is not really very accurate. Like, it doesn't really separate these classes well. And that is because what we find here in the labels, basically it can be because the generative model struggles to learn how to accurately combine these weak labels in a good way. So yeah, there are just some errors in these labels that then propagate to the discriminative model. So this is the problem that we want to address. And we do that by introducing some additional expert knowledge. And yeah, the approach that we took was to using an active learning approach, determine which data points would be useful to label individually, so that we can try and improve these labels. So we start with our generative model, like a part of the pipeline where we learn the generative model and get the resulting probabilistic labels. And then the first step, like in active learning, is to sample a data point using some sort of strategy. So let's say we sample this point, and then we ask our expert what the true label should be. So say the expert said true label is 1. And then to close the cycle, we want to use this true label to learn how to recombine these different weak labels or labeling functions into a better model, so that we improve our probabilistic labels. So that's the general idea of how we sort of combine this framework of weak supervision with active learning. And I'll first show what the result is will be in our simple example. So starting with our end results that I showed, where we have this rotated decision boundary. After some number of active learning iterations, where every iteration we add the label for one data point, we find that we are able to adjust some of these probabilistic labels that are given by the generative model, so that we can learn a better discriminative model. So using those few data points where we get additional feedback from our experts, we can fix this problem where we're basically not able to accurately combine the labeling functions that we have defined. So now we want to look at how many data points do we need to label to get these better results, and how does this compare to other approaches that we could take. So to do that, we first look at the synthetic data, or like a larger sample, just a larger sample of this example that I've been showing. And we look at what happens with the performance for the first 30 iterations, where every iteration we get 1 point for both the generative model. So that's just the performance that we get if we take the most likely class as given by the probabilistic labels, as well as the discriminative model that was given by the decision boundary. And we'll look at the left 2 plots first. Now we start with this baseline for weak supervision, which just stays the same because we're not adding any label points. So this is the performance that we start with, these first two images at the top. And with our method that I just showed, that's adds active learning, which we call active WeaSuL, the dark blue line. We start from this initial weak supervision performance, and quickly, as we start adding label points, we're able to improve the performance of both models to essentially the optimal level that we can get within only a few points. So yeah, that's a quite big improvement compared to just weak supervision. But then for active learning, of course, we don't start out with this initial information that we get from weak supervision, which we have in active WeaSuL, this cycle. So active learning needs some time to catch up, but then really quite quickly also reaches this optimal performance level, because of course it's a quite relatively simple problem. So the difference really lies in here at the start, where our active WeaSuL method has this advantage of starting with the information from the labeling functions. And finally, we have another approach we can compare to, which is basically like a competing approach from a different paper, because they also combine active learning with weak supervision. But apart from that, their approach is quite different. And what we see there for this problem is that because our performance really improves quite quickly, in the first iterations for this approach, we can't really see much improvement yet. So therefore, here on the right, we extend these discriminative model results to way more iterations. So we add up to 1,000 points out of the whole data set. And here we see that it slowly increases performance. But still, at the end, we're not even close to what we get here very quickly. So yeah, it does provide an advantage because we need way less data points that need to be labeled. Now, apart from synthetic data, we also tested this method on a few real data sets. So first on the left, for a spam detection task, we compare the active WeaSuL method to the same kind of baselines. And again, we find that really quite quickly, compared to weak supervision by itself, the orange line, we're able to improve the performance within only a few labeled points. Again, at some point, active learning by itself also catches up to reach the same performance. And the competing approach does a little bit better, but yeah, again, needs more labels to reach a good performance. Now, for a different data set, an image task, it looks a bit different, because first here at the start we see that with weak supervision, so the orange line, we start quite a lot lower. So we're not doing that well in the beginning. So therefore, it's especially useful to try and improve this performance. And we see that it works here as well. So within approximately 15 labeled data points, the active WeaSuL method sort of improves the performance quite a lot. But then comparing to active learning, it's a bit slower again. But eventually active learning by itself, so without any weak supervision, overtakes this method. So that's quite interesting, because it shows that because of how we combine active learning with our fixed weak supervision setting, so we rely on the labeling functions that we have defined, there can be a limit to how much we can improve the performance. So at some point, if we have a large labeling budget, it might just be a better idea to just use active learning, because we're not limited to what we how we define the labeling functions. So in all of these examples, we've seen that this combination of active learning with weak supervision is really very useful if the labeling budget is really very limited, so you can only label a few points. Then we see a quite large performance difference. So then it can be useful to make use of this warm start that we can get by quite easily defining some labeling functions. All right. So now that we've seen that it works, I will show a bit more how it works. So there's a few different components that are important here. So looking again at this cycle I've introduced, the first step, starting from weak supervision, is to determine which point we need to sample. So yeah, like we saw in the previous talk, there's a lot of different approaches we can take here, but depending on the problem, it's really important to find a good one that really chooses the most informative points so that you can improve the performance the fastest. But our setting is a little bit different, because instead of like a pool of unlabeled data points, we actually have these probabilistic labels for our data sets already, and we want to choose from there which of the points would be useful. So to show how we do this, I'll first note that because of how these labels are created, so they're conditioned on the different weak label values or the different labeling function outputs, we get this distribution where the data points are sort of all in different regions where the labels are all the same, because the labeling function divide up this input space, and within a single region, they all output the same value. So we call these different buckets, and actually our problem is then just choosing a useful bucket to sample from, because the labels are all the same. So if we just choose a useful bucket, we can pick a point from there. And then the key idea that we use to determine a sampling approach is that our goal is that within a bucket, the resulting probabilistic labels that we get reflect as closely as possible the actual true distribution of classes within that bucket. So given that, what we do is we compare these probabilistic labels that we got from the generative model within a given bucket to the distribution that we get if we take only the sampled points. So the sampled point, the points that we've sampled so far as part of our active learning process. So these are the true labels that we've obtained. So for example, for this bucket, the generative model gave probabilistic labels of 0.28, so quite close to 0, while actually in the true labels, they're mostly class 1. So there's quite a big difference. And yeah, we use the idea that if there's still like a big difference between these two distributions, it would be quite useful to sample from this bucket, because we're not really sure if what the generative model said here is accurate. So we quantify that using KL divergence for each of the individual buckets, and just rank them according to that, where we can just pick the bucket with the largest value. So that's we pick the bucket where the probabilistic labels disagree the most with the true samples that we have. And we compare this approach, which we call MaxKL, the dark blue line, to a few other sampling methods. So margin, where we sample based on uncertainty of the probabilistic as given by the probabilistic labels, or random, where we just sample, pick a random bucket. And what we find in terms of performance is that the other two approaches apparently are more likely to sample less informative points, which makes sense because, for example, the random approach can pick a bucket that where it's already quite certain that it's really one of the classes. So yeah, it doesn't really help to sample from such a bucket. And to see a bit closer what the difference between these approaches is, we also look at the diversity as measured by entropy of the sampled buckets so far. So if the entropy is high, means that we've sampled a lot of different buckets, so explored a lot. If it's low, we sort of are more stuck sampling from the same buckets. And this is often a problem with the margin approach because, quite often we found that you can get stuck sampling from the same area, which doesn't really, then you don't really explore enough to try and improve the model. Okay, so that's the first component. And then after sampling this point that has been chosen according to the strategy, we get the true label. And then the final step is to use the value of this true label to readjust this generative model so that we can actually improve our probabilistic labels. So how we do that by just starting with the objective that we have for the generative model. and the same labeling functions, but then also adding a penalty for every point that has been labeled. And this penalty sort of makes sure that the outputs that from the generative model more closely reflects the true labels that we found. So the penalty, therefore, the penalty measures the difference between this true label and the probabilistic labels that are given by the generative model. So yeah, by adding a penalty for this difference, we make sure that the generative model is nudged towards giving an output that is closer to what we actually have found from the samples that were added by active learning. Yeah, so that's the main idea that helps us actually use these label points to get these better to get a better generative model that combines the labeling functions and then also better labels and a better discriminative model performance. All right, so to conclude quickly, in many problems, it's difficult to get enough labeled data for your model. So it's a good idea to try and use your expert knowledge as efficiently as possible with techniques like active learning and weak supervision. And we have shown with our method that can be useful to combine these ideas to get better labels and therefore a better predictive performance. And it's especially useful in settings where it's very difficult to label. So the budget is really very limited, because then we've seen that we can get the best performance increase. Okay, so I'm not sure if we have a bit more time for questions.
Cool. Yeah, thanks a lot, Samantha. Of course I know the problem, but what I really like about your presentation and comparing it to the, if you compare it to the first one, is that you see that if you use if you convert the business knowledge into weak labels, that it really gives a big kickstart to active learning. I think that's really interesting. I'm checking if there are any questions online. I don't see anything. Maybe I'll wait. I do have actually 2 questions for you. Your project at WBAA is over, but if you would have a couple of months more time, this is a new technique. What possibilities do you see to improve this new technique further?
Yeah, there's quite a few things. I guess, so the first issue is that, of course, so for this penalty, we've seen in experiments that it has to be balanced with this loss term. So it has to be scaled by some sort of parameter, but of course it's without labeled data, it's very difficult to tune that. So that's, I think, the first issue that would be interesting to look into further.
Okay, there's another question. And the question is, did you already apply to some specific problems in ING? Or maybe I can broaden that question by, is there a specific problem in ING that you would like to apply this problem to, if you got the chance?
Yeah, no, it hasn't been applied to a problem at ING. Sorry. Yeah, I think there are probably quite a lot of interesting applications, but there's probably a bit more research necessary towards like how this works in different, more complex kind of problems, because it is quite maybe difficult to evaluate. But yeah, like I think quite often where weak supervision is used or active learning only would be interesting.
I think the potential for this technique can be very big. If you have a limited budget to get labels, but you do have some business knowledge that can give inaccurate labels, I think this is a very interesting combination. Okay. Okay, yeah, I think we need to move on. Thanks again, Samantha, for a nice talk.